A very good morning to sir and my fellow friends. So today I will go represent the topic Nash equilibrium. So my name is Q Chao-Ming and matrix number was 271311. So what is the concept of Nash equilibrium? So Nash equilibrium is a set of strategy or action such that its pressure is doing the best it can given the action of its opponent. So what is the reason say that the corner equilibrium is same as a Nash equilibrium? So corner equilibrium is the firm. No firm have an incentive to change its output unilaterally because each firm is doing the best it can given the addition of its competitor. So here's the example for the dominant strategy and the Nash equilibrium that you can clearly see the difference. So for the dominant strategy, usually the company is doing the best they can do no matter what other competitor do. But competitor doing the best you can not matter what the company do. So we can do a conclusion about this is that for the dominant strategy, the company won't care about the other's competitor. But for the niche equilibrium, the company will do the best what the competitor doing. So the conclusion do for the niche equilibrium is the company will do the best decision based to the competitor. So here's the example for the product choose problem to show up which is the niche equilibrium. So here's the two firm which is included in the market of cereal market. So for the cereal market there's a two variation which is crispy and also a sweet. So when the firm one want to produce a crispy cereal, so the firm two will produce for the sweet cereal. So when you want produce a firm one want to produce a sweet cereal, the firm two will produce a crispy cereal. So this kind of situation we will call it the niche equilibrium because both company or firm will get the benefit. But when firm one and the firm two produce a crispy cereal in the meantime, they will get loose together. So that is all my part, and I will to my partner to continue.
Alright, greetings everyone. My name is Go Yong Seng and my matric number is 271641. So I will now continue the presentation from my teammates. So here, I will give you an example of the beach location game. So in this case, let's imagine that the sun buffers are spread evenly across the beach, the 200 yards. So they are spread evenly. And then you, represented by Y, and your competitor, represented by C, are selling actually the same products at the same price. So if we think logically, all of the some after they will of course go to the vendors that are the closest to them. So what if, for example, your competitor set the location of its vendor on the point A here, right? On point A. So if he set the location on point A, he can get the customer on the right side of the point A. And then let's say if you set your vendors on the left side of the A, you will get around 3 per 4 of the customer, and your competitor will only got a 1 per 4 of them. So in this case, we refer it as a Nash equilibrium. Nash equilibrium will happen in this case. Why? Because both of you will keep on changing the location in order to maximize the profit. So let's say on the first day you are selling at the left side, and then your competitor, he saw you make a lot of profit. Of course, he will try to change to your location, right? And then you will try to change the location again. So this is what we call as a Nash equilibrium instead of a normal equilibrium. So secondly, it's about the maximum strategy. So before we start, what is actually a maximum strategy? So to be simple, it's a strategy that maximizes the minimum gain that can be earned. And this is considered as a conservative way instead of a profit maximizing way. So here we have another example. I have another example for all of you. So imagine that there are two firms, firm 1 and firm 2. They are both selling the file encryption software which use the same standard. That means if someone buy from the firm 2, it can be used by the firm 1 as well. I mean the software encryption standard, okay, because they are using the same standard. So here, in this case, we assume that firm 1 entered the market earlier, and so logically they have a larger market share. So in this case, both firms are going to decide to make investments to design a new encryption standard. So in this case, we need to know that actually investing is the dominant strategy for firm 2. But there are two possible outcomes that will cause, there are two possible situations, that can cause a different outcome. So let's see. So here is a situation 1. So in this situation 1, we assume that the firm 2 makes a rational choice, which is making investment. So if he makes investment, now we can look at the table. If firm 2 makes investment, he will get $10 million regardless of firm 1, that either firm 1 invest or do not invest. Firm 2 will always get a $10 million increase. So let's say, as for the firm 1, if the firm 1 didn't make any investment, he will lose $10 million. But oppositely, if he make the investment, he will get a 20 million on the other hand. So in this case, in situation 1, the best choice is for the firm 1 to make investment. However, what if firm 2 suddenly decide not to make any investment? So in this case, if the firm 2 didn't make any investment, they will get nothing. They get nothing and they also lose nothing. However, in this case, if firm 1, they decide to invest, they will lose $100 million. So which is why in this case, the best choice for the firm 1 is to not invest, to not make any investment in this case, to avoid the loss. So as an overall, we can see here the maximum strategy for firm 1 is to avoid any investment. Because if, let's say, the firm 1 didn't make any investment, what is the highest loss? The highest loss is only $10 million, right? It's either no change or loss of $10 million. But if suddenly firm 1 decide to invest, what is the highest gain possible for the firm 1? It's only $20 million. But if suddenly in this case, firm 2 suddenly decide not to make any investment, the firm 1 will lose $100 million. So in this case, let's compare. A $10 million loss and a $100 million loss, which one would you go for? Of course, the safest strategy and the maximum strategy is to go for the loss of $10 million. So that's it for my part, and I will now pass it to my teammates. Thank you.
Good day, sirs and my friends. My name is Lee Jun Kang, metric number 269516. I'm going to talk about the maximizing the expected payoff and the prisoner dilemma. Maximizing the expected payoff. It is a strategy in game theory where a player makes a decision that yields the best for the worst outcome. All decisions will have costs and benefits, and a maximum strategy is one that seeks out the decision that yields the smaller loss. If firm 1 is unsure about what firm 2 will do but can assign probability to each feasible action for firm 2, it could instead use a strategy that maximizes its expected payoff. For example, firm 1 thinks that there's only a 10% chance that firm 2 will not invest. In that case, firm 1 expected payoff from investing is 10% times negative 100 plus 90% times 20 equals to $8 million. Its expected payoff if it doesn't invest is 10% times 0 plus 90% times negative 10 equals to negative $9 million. In this case, firm 1 should invest as it will get $8 million. You can see that firm 1 strategy depends critically on its assessment of the probability of action by firm 2. Determining this probability may seem like a tall order. However, firm may face uncertainty over market conditions, future costs, and the other behavior of competitors, and must make the best decision based on probability assessment and expected value. While for the prisoner dilemma present a situation where two parties separated and unable to communicate, must each choose between cooperating with each other or not. The highest reward for each party occur when both parties choose to cooperate. The example goes like this. Two members of a gang of bank robbers, Dave and Henry, have been arrested and are being integrated in separate rooms. The authorities have no other witness and can only prove the case against them if they can convince at least one of the robbers to betray his partner and testify to the crime. Each bank robber is faced with choice to cooperate with his partner and remain silent, or to defect from the gang and testify for the prosecution. If they both cooperate and remain silent, then the authority will only be able to convict them on a lesser charge of jail, that is the 1 year jail for each of the person. If one testify and the others no, the one who testified will go free and the others will get 3 years jail. However, if both testify against the other, each will get 2 years in jail for being partly responsible for the robbery. In this case, each robber always have an incentive to defect regardless of the choice that the others make. From Dave's point of view, if Henry remains silent, then Dave can either cooperate with Henry and do a year in jail or defect and go free. Obviously, he would be better off betraying Henry and the rest of the gang in this case. On the other hand, if Henry defect and testify against Dave, then Dave's choice become either to remain silent and do 3 years in jail or to talk and do 2 years in jail. Again, obviously, he would prefer to do 2 years over 3. In both cases, Henry cooperate with Dave or defect to the prosecution. Dave will be better off if he himself defect and testify. Now, since Henry faces the exact same set of choices, he also will always be better off defecting as well. The paradox of the prisoner dilemma is this: both robbers can minimize the total jail time that the two of them will do only if they both cooperate. Then you will get each year jail for each person, but the incentive that they each face separately will always drive them to defect and end up doing the maximum total jail time between the two of them. That's a 2 year for each other. This is for the prisoner dilemma. That's all from me. Thank you.
My name is Anyo Bingqi, metric number 272146. Now I will present about mixed strategies. Mixed strategy is a strategy in which a player makes a random choice among 2 or more possible actions based on a set of chosen probabilities. In all of the games that we have examined so far, we have considered strategy in which players make a specific choice or take a specific actions. For example, advertise or don't advertise, set a price of $4 or a price of $6, and so on. Strategies of this kind are called pure strategies. However, there are games in which a pure strategy is not the best way to play. An example is the game of matching pennies. In this game, each player chooses heads or tails, and the 2 players reveal their coins at the same time. If the coins match, player A wins and receives $1 from player B. If the coins do not match, player B wins and receives $1 from player A. The payoff matrix is shown in this table. Note that there is no Nash equilibrium in pure strategies for this game. Suppose, for example, that player A chose the strategy of playing heads, then player B would want to play tails. But if player B play tails, player A would also want to play tails. No combinations of heads or tails leave both players satisfied. One player or the other will always want to change strategies. Although there is no Nash equilibrium in pure strategies, there is a Nash equilibrium in mixed strategies. In this game, for example, player A might simply flip the coin, thereby playing heads with probability 1/2 and playing tails with probability 1/2. In fact, if player A follows these strategies and player B does the same, we will have a Nash equilibrium. Both players will be doing the best they can given what the opponent is doing. Note that although the outcome is random, the expected payoff is 0 for each player. It may seem strange to play a game by choosing action randomly, but put yourself in the position of player A and think what would happen if you follow a strategy other than just flipping the coin. Suppose you decided to play heads. If player B knows this, she would play tails and you would lose. Even if player B did not know your strategy, if the game were played repeatedly, she could eventually discern your patterns of play and choose a strategy that countered it. Of course, you would then want to change your strategies, which is why this would not be a Nash equilibrium. Only if you and your opponent both choose heads or tails randomly with probability 1/2 would neither of you have any incentive to change strategies. That's all from me. Thank you.
My name is Liu Jiaying with matrix number 271795. So let me continue to explain the battles of the sexes. Okay, this game is go like this. James and Tony are plans to spend their Sundays together, and they both of them have different activities. James prefers to go to swimming, while Tony's prefer go to play basketball. Therefore, the payoff matrix will be formed as this table you see. Okay. In this table, they have two Nash equilibria in poor strategy, which is James and Tony's. Both of them go to swimming. And the other one is James and Tony's. Both of them go to play basketball. Obviously, James will choose outcome 1, which is go to swim together, while Tony will choose outcome 2, which is play basketball together. But in this, for example, if James and Tony go to swimming, it will cause Tony cannot enjoy in this activity because the payoff is 1, while James will enjoy in this activity because the payoff is 2. Same as the outcome 2. James and Tony go to play basketball. Tony will enjoy in this activity because the payoff is 2, while the James will not enjoy in this activity because the payoff is 1. So in these situations, there is no equilibrium. By solving these solutions, we can use mixed strategy, which is the payoff should be at least 1 that can assist the expected payoff 2 per 3. That's all from me. Thank you.